temperature. So the equilibrium constant changes with temperature. It's also true that rates of reaction change with temperature. And kinetics is our last unit in this course, and we'll be discussing that quite a bit. So how does the equilibrium constant change with temperature? Let's consider that. So let's look at some of the equations that we know that have delta H in them. Delta H, again, is our predictive factor when we're talking about changes in temperature. We know that delta G naught is minus RT, natural log of K. So the relationship with our standard free energy, our gas constant temperature, and our equilibrium constant. We also know that delta G naught equals delta H naught minus T delta S naught. If those equations don't look familiar, then you should go back and review the material on thermodynamics, because you're going to need it in this unit, the next unit, the unit after that, and then the next 2 units, and then we're done with the class. All right, so good to get familiar with this now. All right, so we can rearrange these in terms of solving for our equilibrium constant. And so we see the natural log of the equilibrium constant minus delta H naught over RT plus delta S naught over R. And so it's reasonable to assume that for the things we're talking about, that delta H naught and delta S naught are pretty much independent of temperatures. That would be true for pretty much any temperature we would be talking about. So that means that K, or the natural log of K, is going to change depending on the temperature. It won't change. These other ones are constant at all the temperatures, so there's a relationship between the equilibrium constant and temperature. So you can consider an equilibrium constant at one temperature and an equilibrium constant at another temperature. So we can talk about the natural log of a K2 of an equilibrium constant 2 equal to minus delta H over RT temperature 2 plus delta S naught over R. We can do the same thing for another temperature 1, equilibrium 1. And if we subtract these two, delta S is going to cancel out, and we're going to get this equation, which you know is important because it has a name. So this is the Van Hoff equation. And at some point later in the course, I'll be asking you to come up with this name. So I always get very excited when people can tell me it's a Van Hoff equation later on. Not that that's on a test, but there are very few equations that have names. So here we go. So what does this do? Well, we can talk about the natural log of one equilibrium constant over another, an equilibrium constant K2, which is the equilibrium at temperature 2, equilibrium constant K1, which is the equilibrium constant at temperature 1, is going to be equal to minus delta H naught over R, and then it depends on the temperature. So you bracket 1 over temperature 2 minus 1 over temperature 1. And this just comes from subtracting those two equations. So again, you can think about how the equilibrium constant is going to change with temperature. That's what this equation does for you.